students, today we're doing lesson 9.3. You guys get the inverse function. So remember, inverses can be written as f of x if that's a function, and then the inverse function would be written as f with that -1. So that's the inverse of x. See how it swaps? Recap from yesterday. So yesterday we were factoring the rationals, and then we were seeing if there was any points of discontinuity. We were graphing it. So that's where we want to start. So it says sketch the graph of the following function and determine the following characteristics for each function below: the domain, the x and y intercept, the equation of the vertical asymptotes. I'm also going to do that the point of discontinuity as well. At the bottom, we can factor the difference of squares as x minus 3, x plus 3. So what you'll notice is that these two factors cross off. So we know that there is going to be a hole at x equals -3. So the point of discontinuity is -3, and let's look at the y coordinate. We know what's left over is 1 over x minus 3. So if we plug in x as -3, we get 1 over -6. So we know that this is our y coordinate for our point of discontinuity. X-intercepts. Well, we have 1 over x minus 3. There is no k value in this case, so the k value is 0, which means that there is a vertical and horizontal asymptote. So there's a vertical asymptote at x equals +3, because that's what's left. So if we look at this value here, the non-permissible value is 3, so there's a vertical asymptote at x equals 3. There's a horizontal asymptote at y equals 0, which means that there's no x-intercepts. So there's no x-intercepts, which is why I wanted to find the horizontal asymptote first. Let's look at the y-intercept. The y-intercept, if I make x equal to 0, is going to be 0 plus 3 over 0 squared minus 9. That's going to be 3 over 9, which simplifies to -1 over 3. So the negative came from the -9. So -3 over 9 simplifies to -1 over 3. So with that information, I'm going to start plotting that information. I have a vertical asymptote at 3. No x-intercept, which means that there's that horizontal asymptote at y equals 0. We also have a y-intercept of -1/3. And we have a hole at -3 and -1/6. So what I'll do is I'll start connecting those with the arrow. And then once I reach that asymptote, I'll change direction and go downwards. Now if I graph this function, I'll know that there's still a part of the graph in this part right here. So I'm going to also draw that shape, making sure I get close to that asymptote but not touch it. The domain. Once I draw it, I like to do domain and range. The domain is x such that x cannot equal. We have two values that it's not allowed to be equal to. So we have that point of discontinuity, -3, and that vertical asymptote. For our range, y such that y cannot equal -1 over 6, and it can't equal 0, y here. So the -1/6 came from the y-coordinate of the point of discontinuity, and the 0 came from the horizontal asymptote. Make sure you label your numbers. There you go. Okay, so in lesson 9.3, we're connecting graphs to rational and rational equations. So there's going to be a little repeat from 20-1 where we have to create equations and graphically and algebraically solve for rational equations. So when we algebraically do this, when we solve for solutions, we're going to have to check for extraneous roots. Those are answers that if we plug them back in, left side doesn't equal right side, or they don't make sense. So solving a rational equation graphically means finding the x-intercepts or the point of intersection. If you're finding the x-intercept, that means your equation was equal to 0. If you're finding the point of intersection, that's where you go y1 for the left side and y2 for the right side of the equation, and you want to find where they intersect. So those are two different methods for graphically solving for a rational equation. If you're algebraically doing it, you want to factor the denominator, state the non-permissible values. You want to determine the lowest common denominator. You want to multiply every term on both sides by the lowest common denominator. You want to solve for the variable and always check your answers. So let's look at this first example. Let's do this one. Let's determine the roots of the equation algebraically. So what I like to do is I like to get a common denominator for each. Okay, so if I'm multiplying the bottom by x, because there's nothing there, I have to multiply the top by x as well. So that's what I just inserted. Same thing with the 5. If I'm multiplying this guy by x, the bottom has to also be multiplied by x. The goal is that you want a common denominator with all your terms. So all your terms, all your little fractions have to have common denominators. Okay? Now what we can do is we can multiply both sides by that lowest common denominator. Now I would do it on this side as well, but when anything multiplied by 0 gives me 0, so it's not really necessary to do it there. But if there was a number other than 0, I would have to do that, okay? Now, once you have that done, you're going to multiply the entire expression by x, okay? What that does is it crosses itself out. It crosses all of these guys off with this one, okay? So as long as you do it to all of it, all of the equation, the left side, right side, it's still equivalent.
Ms. Pascal, please come to the office. Ms. Pascal, in the office, thank you.
So you have 14 minus x squared, you did not cross off the top, so that's going to be x squared now, plus 5x equals 0 times x is 0. Now you'll notice that this is a quadratic equation, so we're going to have to get everything on one side, which it is. I prefer to bring everything where the side where the x squared is positive, so I'm going to move everything to the right side actually. So I'm going to have x squared minus 5x minus 14. This I can actually nicely factor, so that will help me solve for my x-intercepts or my x values. So it'll be x minus 7 times x plus 2, which will give me that the x-intercepts are 7 and -2. Now, since I algebraically did this, I need to check. Now, to check, you can always do this graphically. So what I'm going to do is I'm going to go to my graphing calculator, and I'm going to graph what I saw, and I'm going to see if it matches my solution. So this is the graphical approach. So we're going to determine the x-intercepts of the graph by graphing this into y1. So since everything's on one side, you can graph everything as y1. So I have 14 over x minus x plus 5. I'm going to use the standard window. Now, I don't really have to find them just to see, but do you guys see how the x-intercepts, just by looking at it, are -2 and +7? They match the solutions that I had algebraically, so these are both solutions. The graphical solution will always show all the real answers, okay? Algebraic can sometimes have extraneous solutions, graphical cannot. So what we'll do is we'll sketch this right now. This is the graphical approach, is drawing a point at -2. It looks something like that. This is our x, this is our y, and here -7. Okay, so we knew that we got the same answers as we did algebraically. So that's a way that we know that we're doing it properly. So in C, they want you to determine the connection between the roots and the x-intercepts. Well, they are the same. You should always find that the x-intercepts of the graph and the roots are the exact same thing. If they're not, that could mean that your algebraic has extraneous solutions, which is why you need to check your answers. Okay guys, let's go through example number 2. So example number 2, I'm going to solve this graphically first. So we're going to express the answer to the nearest hundredth, and then we're going to verify our answer algebraically. So I'm going to start by putting this into my graphing calculator. So with this one, when I'm doing this graphically, I am going to label this as y1. The left side I'll label as y1, the right side of the equation I will label as y2. So that's what I'm going to do in my graphing calculator. Clear whatever you have there. For y1, you're going to go 2 minus, in brackets, 3x divided by 2. The y2 is going to be in brackets 1 plus 4x squared minus, it should be actually 4x. So it's 1 plus 4x minus x squared. Close your bracket, divided by, in brackets, 4x plus 10. Graph this. Okay, so there is our linear equation, which is our y1, and this is our y2 value. So I'll go second trace. I'll go to the intersection, number 5, and then you're going to go as close as possible to the intersection you choose, and you're going to press enter 3 times. So our first answer is -3.34. So we know that we're going to have an intersection at x equals -3.34. Okay? So we're only looking at the x coordinate when we're solving for these. So the x coordinate. Second trace, we're going to go to number 5, the intersection, the second one. We're going to move our cursor as close as possible. We're going to press enter 3 times. Enter, enter, enter. We get 1.14. So positive 1.14. Now what I'm going to do is sketch this. So I'm going to go to my second graph, my table of values, and I'm going to plot a bunch of points and then sketch that. So that's what I want you to do right now is graph those points. Okay, so with this, if I were to factor the bottom here, I have 2 in front of 2x plus 5. That tells me that I'm going to have a vertical asymptote at -5/2, so that's -2.5. So -2.5 on that side, I'm going to have that vertical asymptote. Okay, so we also, when we're graphing this, you're going to see something like this occur. We're going to make sure that our graph goes through the point of -3.34 and 7. So when I looked at the coordinates, it was -3.34 and +7. So that's where the graphs are going to intersect. So I'm going to do one of the graphs over here. So one of them should look like this. And then that same graph, if you were to graph it, will have this kind of look as well. It's going to be close to that x, that asymptote, and then go away from it over here, that vertical asymptote. Then we have a linear equation. So the linear equation will have a y-intercept of 2. So this is the y1. And it's going to go through these points, that point that we intersected with. And it's also going to go through the point of 1.14, so approximately there. I'm just going to draw a straight line going through it. And this is what I want to show, is that these 2 points are my answers, the intersection of both. Okay, so that is the graphical approach. Our answers are rounded to the nearest hundred, so that's what we have to do. B, we want to verify our answer algebraically. So to do this algebraically, we're going to have to factor the denominator and get our lowest common denominator. The top I'm not going to touch. The bottom though, I'm going to factor as 2 bracket 2x plus 5. So I'm dividing the 2 out from those terms. And that shows me that since I already have a 2 for the fraction over here, it's just missing the factor of 2x plus 5 to be common. What I do to the bottom, do to the top. This one here is missing both. It's missing a 2 in the bottom and a 2x plus 5 to be common. So what you do to the bottom, do to the top. Now we're going to multiply the entire equation, the left side and the right side, by 2 bracket 2x plus 5. Okay? And what that will do is it will cross off all the denominators in the entire equation. So what you're left with is 4 needs to multiply with 2x plus 5, minus 3x needs to multiply with 2x plus 5, and on the right side, we have 1 minus 4x minus x squared. I'm going to distribute that 4 into the brackets and the negative 3x into the brackets as well. We have 8x plus 20 minus 6x squared minus 15x equals 1 minus 4x minus x squared. Now I'm going to bring everything to one side because it's a quadratic equation. So I will bring this negative 6x squared to the other side by adding positive 6x squared, and to this one, positive 6x squared. That will cross off. Then I'm going to subtract 8x to both sides, subtract 8x, and then add 15x, add 15x. So I'm just doing this all in one step, and then finally subtract 20, subtract 20. So on the left side, we're going to have 0. Then I'm going to combine the x squared values first, because I like in standard order. 6x squared take away x squared will be 5x squared. Then negative 4 minus 8 plus 15, put that in my calculator, is equal to I just saw an error, guys. This should be a positive 4x. This should be a positive 4x, which means that you should have 4x. There you go. That's the mistake I was looking for. So 4 minus 8 plus 15 gives me 11. Okay, that makes more sense. So we should have plus 11x. And then we have 1 minus 19, which is minus 19. There you go. So now, with this, we have A equaling 5, B equaling 11, and C equaling negative 19. I'm going to use the quadratic equation to solve for my x intercepts. So we're going to have negative 11, that's x, equals negative 11 plus minus 11 squared minus 4 times your a, which is 5, times your c, which is negative 19. Divide the entire equation by 2 times a, which is 5. So if you put this into your calculator, I'm going to have negative 11 plus minus, I'm going to take the square root of, in brackets, 11 squared. I'm just putting that into my calculator. I get that this is 22.383. Divide that by 10. You should get two answers because you're going to add the numbers and you're going to subtract the two numbers. So I get 1.14 if I round to the nearest hundredth, and so that's with adding them. With the subtraction, I get negative 3.34. So exactly the same answers that I got graphically. So that's what you should find, is both answers work. Both answers are correct, and that is how we verify. Example number 3. Okay, so we want to do this algebraically and graphically. So for A, algebraically, I'm going to factor the denominator. Now the bottom, I'm going to rearrange it. So it's going to be negative x plus 3. The reason is I want it to look like the other one over here. And right now they don't. So there's a little trick that I do whenever I see the exact same numbers but the wrong signs. So what I'll do over here is I'm going to factor out the negative. That means take out the negative, and that changes both sides within your bracket. And if you look at it, now you have two negatives. A negative and a negative dividing becomes a positive. So I'm going to rewrite that to write it as one symbol instead. So you're going to have plus in between of x over x minus 3. And now we have the exact same factors. This simplifies our work a lot in the long run. So this is something we always want to do if we have the same numbers but the wrong signs. So now I want to get common denominators. This guy is missing the 2, so I'm going to multiply the bottom and top by 2. This one is missing the 2 and the x minus 3 to the top and bottom. And the step that we do next is we multiply the entire equation by the common denominator, which is 2 and x minus 3. What that does is it crosses off all the bottom and this top numerator. So what you're left with is x plus 3 on the left, and then we have 2x times x, or 2x times 2, which is 4x multiplying by x minus 3, and then we have 2x. When we expand, when we get rid of the brackets, we distribute the 4x in, and that gives us 4x squared minus 12x plus 2x. Now we're going to bring everything to one side, but we're also going to combine these two as well. So we're going to have x plus 3 equals 4x squared minus 10x when we combine the negative 12x and the positive 2x. Here we're going to subtract x, that gets rid of that. And we're going to subtract 3, subtract 3. So now we have 0 on the left side, we have 4x squared minus 11x minus 3. So we're going to factor this. This is where we want to find two numbers that multiply to the outsides and add to the middle. So I found that the factors were 4x plus 1 multiplied by x minus 3, and that equals 0. That means x equals negative 1 over 4, and x could equal also positive 3. Now, if we look back at our original question, what are our NPVs? It's always best to look at them when they're in factored form, and in this case, x is not allowed to be 3. So if we look, our answer here of 3 is not allowed. That is an extraneous solution, which means that the only solution that is possible is -1/4. So in this question, we actually have a vertical asymptote occurring at x equals 3. So we're going to draw this dotted line at x equals 3 because the graph is not allowed to go through that, right? There is no answer there. So if we were to graph this as y1 and this is y2, I just want to show you what that would look like, and then we're just going to sketch it. But for a good sketch, we always want to go to that table of values, right? So in brackets, we're going x plus 3, close your bracket, divided by 2x minus 6. The right side, or that was the left side, now the right side is 2x subtract x divided by bracket 3 minus x. So what it looks like is this. So we'll actually have a horizontal asymptote at 1/2. So if you guys look at the values in front, remember the leading coefficient, they equal 1/2. So we're going to have a horizontal asymptote for the left side go right there. So we're going to stay right close to that line for the y1. And then we're just going to go away from it. So that's 1, and the same thing will happen over here. Okay, so that is y1. y2 is going to have a strange shape as well. So it kind of goes, it's like a curved quadratic function. So it looks something like this. There you go. So what we should find is that these guys don't intersect except for the point right here. It intersects at the value of -1/4. When x equals -1/4. This is your x, this is your y. You would label the numbers down. And you just want to show that clear intersection between the two graphs at -1/4. And that's how you check your answer. So you should always find that you're getting the exact same answers. So if this graph doesn't show an intersection of 3, it's because it isn't a solution. Example number 4. So Megan and her friends are organizing a fundraiser for the local children's hospital. They are asking local businesses to donate a door prize. So far, they have asked 9 businesses, but only 1 has donated a prize. Their goal was to have 3/4 of the businesses donated. If they succeed in getting every business to donate a prize from now on, how many more businesses do they need to ask to reach their goal? This is what their X will represent. How many more businesses are they going to ask? So this is what X represents. So what we know so far is that they have asked 9 businesses total, and only 1 has chosen to donate. So we're going to use that fraction, right? But we know that our goal is to have 3 out of 4 donate, a quarter, right? 3/4 of the businesses donate, which is 3/4. Now, that means we're going to add stuff to your total. So instead of our total being 9, we're going to add X more businesses they need to ask. Now, if they're asking that many businesses and they're going to succeed in getting every single business to donate, you're going to have the same value at the top and bottom being added, which is X. So this is our equation that represents solving for how many more businesses do they need to ask to reach their goal. So in this process, you can get common denominators. If we're doing this algebraically. So what the left side is missing is the 4. What you do to the bottom, do to the top. What the right side is missing is the 9 plus x, because it already has 4 at the bottom, so it's missing 9 plus x. Now we're going to multiply both the left side and the right side by the common denominator of 9 and 4. 9 plus x and 4. And what that does is it crosses all of these off. So it crosses off your denominator, leaving you with, if I distribute, 4 plus 4x equals 27 plus 3x. Now we're going to bring the x's on one side, numbers to the other side. So I'm going to have 4x take away 3x, because I brought the 3x over by subtracting. And 27, I'm going to subtract 4 to it. So that's going to give me x is equal to 23. That's our only solution, which means that they have to ask 23 more businesses, and they all have to agree to donate in order to meet this goal of 3/4 donating. So that's our solution. Example number 5. The speed of a boat is in still water is 10 kilometers per hour. It travels 25 kilometers upstream and 25 kilometers downstream in 6 hours. This equation models the total time for the journey in terms of the speed of the current. So V velocities, or V kilometers per hour, is represented by this equation. What is the speed of the current to the nearest whole number? They want us to solve for V. So we're going to set up a chart here. So we did this back, or we should have done this in 20-1, where we're comparing distance, speed, and time. So we have two things to compare, upstream versus downstream. So up versus down. We know that the distance that they're traveling is 25 kilometers upstream and 25 kilometers downstream. So this is in kilometers. We also know the speed is going to be their speed in still water, and if they're going upstream, they're going to go against the current. So V is going to represent the current. If they're going downstream, the current is going to help them, so we're going to add V. So if you're going upstream, minus V. If you're going downstream, add V. Time is always going to be, if we look at this triangle that we create, distance over speed time. Distance over speed is equal to time. So if you divide these, you're going to get time. So that means 25, which is the distance, over the speed of 10 minus v, that's going to represent the time of going upstream. And 25 over 10 plus v represents the time it takes to go downstream. They're also telling us that the total, because of the word and, is 6 hours. So we're going to add these two equations. So that's how they got that. They added the two times as rational functions, and they got that they were equal to 6 hours. Okay, so here in this case, we can do this algebraically, we can do this graphically. I'm going to switch to the graphical just to show you how to do this one. So you can choose which one you prefer or how you answer the question in these cases if they don't tell you a method. So we're going to put the left side, which is 25 divided by 10 minus x, that's our v, and we're going to add it to 25 divided by 10 plus x, which is our v as well. And that's going to equal 6. So with our window, we're going to have to change our window. We're going to talk about the window is x represents the velocity of the current. You can't have negative speed for a current. So we're going to start from 0 and go to 10 for it to be logical. Y represents the amount of time it takes in total for them to go downstream and upstream. So we actually know that answer, and it's 6. We know that the equation is equal to 6. So we just have to go and use numbers around 6. So I'm using 0 to 10 because 6 is in between. And then you can graph it. So this is the y1. And where it intersects with 6 is what we want to find. Second trace, number 5, which is intersection. Press enter 3 times. you should get to, it says to the nearest whole number, that it will take, the current will be 4 kilometers per hour for this to make sense. So we found this by doing this as y1, this is y2, and the intersection occurred when x equals 4 if it's rounded to the nearest whole number. And so what we just did was we did kilometers per hour. Make sure you include the units for this to be correct. So we can definitely use our graphic calculator to help us once we have the equation. Number 6, so they're giving us, the owner of a manufacturing plant is trying to eliminate harmful emissions. They use the function, it's 200,000 P over 100 minus P to estimate the cost in dollars to eliminate P% of the emissions from the plant. Okay, so what domain is appropriate for this situation and why? Well, the domain that I would use would go from 0 to 100. So since I'm doing interval notation, I would go from 0 up to 100, rounded brackets. The reason I have rounded brackets for 100 is if I put 100 minus 100 in my bottom, so P is the domain, is what we're talking about, then I'm going to have 0 in my denominator, so I don't actually want it to be equal. So not equal to 100, okay? So that's the domain that's appropriate. The reason I started from 0 is you can't have a percent, which is P, being a negative value. Percents go from 0 to 100, okay? So that's why we chose that domain. Now we're going to graph the function. So we know the graph is starting from, if I plug in P as 0 at the top, then that's going to be 0 over 100, which is 0. So I already know that the x and y intercept would be 0. Now for my scale, I actually went up by 30,000. All the way to 300,000. And for the x's, I went up by tens. So I know that if I plugged in these values, I would plug in like a few points. I could plug in when P is 30, what costs are you looking for? And I would plot a few points. So for example, I plotted when I got 20, I got somewhere around here. When I put in 50, I got around, I think it was like 200,000 or something. So you're just approximating, you're going to see that the graph looks like this. So how is its shape related to the manufacturing context? So the shape here, this is actually called an exponential function. We're going to study that in the next chapter, in the next unit, but an exponential function grows very quickly. So this is growing very quickly. Why? Because the more emissions you try to get rid of, the more cost is the manufacturing company will incur. So it's going to cost way more to get rid of certain percents of emissions the higher you go. Okay, so we graphed it. Make sure you include your scales. Does it cost twice as much to eliminate 80% as it does to eliminate 40%? So let's check. Percent is what our p-value is. So they're saying, what if p is 80? And then what if p is equal to 40. Let's plug it into our equation and see what we get. So what is the cost if we go 200,000 times 80 and divide it by 100 minus 80? And then we'll do the same thing for 200,000 times 40 divided by 100 minus 40. You should find that the cost for 40,000 is $133,333.33. So that's the cost for eliminating 40% of emissions. Versus 80% of emissions will cost $800,000. As you can see, it is not twice as much. This is actually 6 times as much. So how I did that is I took this number here and I divided by this number. So I divided the 80,000, the P of 80,000 divided by the P when P is 40, and I got 6 times, approximately 6 times more. So explaining, well, it's not going to be, when it's exponential growth, it's not linear, okay? So it would only be twice as much if it was like a linear function. Exponential functions grow very quickly, so we can expect that the cost would be way more than as we try to increase, or as we try to decrease the emissions from a plant. Now, is it possible to completely eliminate all the emissions according to this model? No, because we have a vertical asymptote there. Okay, so another reason is I think the cost would get way too high once you get to a certain number. So most companies would not be able to eliminate after a certain percentage because the cost would probably outgrow what they're actually making. So most companies, they wouldn't make as much to be able to get rid of all those emissions. And so that is lesson 9.3. Hope you guys have a good day.